Hello and welcome to the fourth video on calculus. In this video, I'm going to discuss the chain rule for partial derivatives. And we're really just going to look at one particular case. You can imagine there are lots of different cases depending on what is a function of what. So you could have a function of, say, two variables, and then each of those variables could be functions of a certain number of variables. And there are many different possibilities for this. Giving rise to different versions of the chain rule, and they can all be unified. But we're just going to look at one particular case here, and then later in another course you'll learn about more general cases. So the case we'll look at, we have a function z. We'll assume it's a function of two variables x and y. And for the chain rule, later on we'll consider that x and y are functions of another variable t. But for the moment we'll just think of this function z of x and y. And so if you make a small change in x, say, and hold y constant, that results in a change in z. And in the linear approximation, the change in z that results from a small change in small change in x, is given by this formula here. So that the change in z, which is this delta z, is approximately the partial derivative of z with respect to x times the change in x. If you divided through by delta x, you would have that the change in z divided by the change in x is approximately the partial derivative. And taking the limit as the change in x goes to 0, that gives you the exact derivative, the exact partial derivative. But for a small finite change, it's a linear approximation. And now if we also change y, so we add the effect of possibly also changing y by some small amount, delta y, then the change in z in the linear approximation is given by this formula here. We simply have the change that would result coming from the change in x plus change that would result coming from the change in y, dz dy times delta y. Okay, so now suppose that x and y are also functions of t. And so in fact z is a composition of two functions. Z is a function of t, but obtained as a composition of z, a function of two variables x and y, and then x and y each depend on t. Then, from the equation from the previous page, the change in z in the linear approximation is approximately partial derivative of z with respect to x times delta x plus partial derivative of z with respect to y times delta y. And then if you divide by the change in t, that gives rise to this small change, you get this approximate formula. And as you let delta t go to 0, this converges to this formula shown here that involves the actual derivatives of x and y with respect to t. And the derivative of z with respect to t is a partial derivative of z with respect to x times the derivative of x with respect to t plus the same thing with x replaced by y. And so note in this formula we are making a distinction between z, which depends on two variables, and so we have the partial derivatives with respect to y and x. And then x and y just depend on t, so we have the straight d's with the non-partial derivatives dy, dx dt, and dy dt. Okay, so this is a chain rule in this case where we have a function z depends on x and y, and then x and y depend on t. Okay, I'm going to look at an example first of the linear approximation that we used on the first slide or 2 slides ago. So that to show you. So this linear approximation here, the change in the quantity z is partial derivative times the change in x plus the partial derivative with respect to y times the change in y. And so we'll do an example where we just work out that approximation in a particular case. And so the case is described here. We're going to model a tree as a cylinder, which is an idealization, of course. And it grows by a certain amount. Its height changes a certain amount each year, and its radius change. And we want to know the change in the volume. So the volume depends on the height and the radius. And these two variables, height and radius, and they each change by a certain amount. So I'll do this by hand. And I've left the exercise up there so you can, or the example up there so you can see it. So we are modeling the tree as just a cylinder, the trunk of the tree, of course. And this has a certain radius. It will call R, and a certain height. We'll call H. And we want to consider the volume of the cylinder, or the volume of the trunk of the tree. The volume I'll write as V. And the volume of the cylinder, well, is the area of the circle at the base times the height. So the area of the circle at the base is pi times the radius squared, and then the height is, so pi r squared h is the volume. So this will be the z that we're interested in, relating it back to the earlier slide. Let's go back and look at that formula. So v will be z, and we want to know the change in v, and we'll use this formula marked as star on that slide. So the change in v in this linear approximation is delta v. And so it is dv r. There are two variables, r and h, times the change in r plus dv h times the change h. And well, in the example, we have quantities for each of these things: the radius, the height, and the changes in the radius and the height. And so the radius is 50 centimeters. Let's write things in meters. So 0.5 meters. The height is 8 meters. Change in the radius in a year, delta r, is 5 centimeters. Is 0.05 meters. And the change height in the year is 1.5 meters. And so we put everything into this formula. We have to calculate the derivatives as well. So let's calculate these partial derivatives. dv, the derivative of v with respect to r, is 2 pi r h. This is dv dr, and times delta r, plus dv dh is pi r squared times delta h. So this is derivative of v with respect to h times delta h. Okay, so we have all the quantities we need, and we have the formula for the linear approximation and the change in the volume. And so delta v, and so maybe I should say really equal sign here to make sure, so emphasize it's an approximation. So the change in the volume is approximately, we have 2 pi r, 2 pi times 0.5 meters times 8 meters times delta r, 0.05 meters plus pi r squared, 0.5 meters squared times the change in h, delta h, times 1.5 meters. Okay, and so now you would put this in the calculator, and I have done that. So you'll get that this is approximately 2.42 cubic meters. So this is the approximation, in the linear approximation for the change in the volume. This example is a bit silly, of course, because you can calculate the exact volume after it's changed this amount, but it's to demonstrate this linear approximation. Okay, I'm going to do one more example, so I'll just move to the next slide. Example 2, using the chain rule. And so what we're going to have in this example is a particle moving along a given path in the xy plane. So that is going to be a function of time. So we have y plane, and we have the particle. The path of the particle is given by x and y, which are functions of t. The little t, lowercase t, is time. Y of t by sine t. Omega, and it looks like a W, the Greek letter, is just a constant. And so this path, well, if you know from trigonometry, you should hopefully know from trigonometry that a particle that follows this path is actually going around a circle of radius 1. So the path looks like is this circle, so it simply goes around the circle and go around in the anti-clockwise direction. So this is the path of the particle. And then at different places in space in the xy plane, there are different temperatures, as stated in the example. So the temperature T is a function of x and y, and it's 200 plus x squared minus y squared. And so what we want to know is what is the rate of change of temperature that the particle feels. And so we have a function of temperature, function t of position. Temperature depends on the position, and then the position of the particle depends on time. And so this is a composition of the function t of the two variables x and y, and then x and y, which are functions of time. And we can calculate the derivative of temperature with respect to time in two different ways. And so let's do it both ways, one using the chain rule and one just by substituting in the formulas for x and y. So the first method, we'll just substitute in the functions for x and y. So if we do that, we have that t equals 200 plus x squared, and x is cosine of omega t, so cosine squared of omega t, minus y squared, and y is sine omega t, sine squared of omega t. And if we want to calculate the derivative of this temperature with respect to time as the particle is moving, and now just differentiate this function of the variable t, lowercase t, time. And so the derivative of 200 with respect to the time t is 0. And we just have to differentiate these other terms. So to differentiate both of these, you have to use the chain rule, because this is a composition of functions, the cosine and then the squared function. This is the chain rule for just normal functions of a single variable. And when you do that, you have this derivative of cosine squared omega t is negative 2 omega cosine of omega t times sine of omega t. And then we differentiate sine squared of omega t. You also have to use the chain rule again, and you get the same thing. Okay, and so these terms are the same. You can add them together. You have negative 4 omega cosine of omega t sine omega t. And, well, this is sufficient for the answer, but you may also recognize that you can use a trigonometric identity, in order to simplify this a little bit more, using the double angle identity for sine. This is negative 2 omega sine 2 omega t. Okay. So this is method 1. We've simply substituted in for x and y, and we haven't used the chain rule for partial derivatives. Just used the normal chain rule that we used from before. Method 2, we can use the chain rule for partial derivatives that we've just covered. All right. So we once again have that t is a function of x and y, and each of x and y depends on t. So I'm going to write them again in order to have them on the screen here. T was this function of x and y, and then x was cosine of omega t, and y is sine of omega t. And so, if we want to apply the chain rule, that I just covered, we have that the derivative of this temperature with respect to time is equal to the partial derivative of temperature with respect to x times the derivative of x with respect to t, plus the partial derivative of the temperature with respect to y times the derivative of y with respect to t. And so now we just have to take these derivatives. So dt dx is 2x. The x dt is negative sine of omega t times omega. Negative omega sine of omega t. Plus dy dt is minus 2y. And I may have said that wrong. dt dy is minus 2y. dy dt is cosine of omega t omega. Okay, and then we can plug back in, substitute in what x and y are here if we want to get everything in terms of t, or in some cases it might actually be more convenient to leave this in terms of x and y. This is the derivative, but in order to check that it gives the same formula as from the other method, let's substitute in what x and y are. So we have 2 cosine of omega t times negative omega sine of omega t. So let's put the negative here. Sine of t omega, and minus 2, and then y was sine of omega t. Cosine of omega t times omega. And well, this was the same formula we had here, and then you simplify the same step, and these two terms are the same. Simplify again using the trigonometric identity as before. Oh, sorry, locked it up. So this cosine of omega t times omega is the cosine of omega t times omega here. Okay, so this is this example. And, well, this is the last example I was going to do just about the chain rule. We will do some sort of similar things next time, looking at error estimates. The application of partial derivatives, we'll look at how you can estimate error when you have a function of two variables and there's error in the measurements of those variables.